Hey everybody, let's continue our study of limits. Alright, for this first example, let's consider and graph this function. Okay, well, without picking up a calculator, we can quickly graph the x-intercepts. So we know the zeros of this function occur at x equals 0, x equals 2, and x equals -3. Zero, 2, and -3. Okay, now from here, what we can do is think about that if you were to perform the algebra and FOIL and distribute, or multiply all those expressions together up here, that would produce a cubic function. All right, and it's a cubic function with a positive coefficient on the leading term. So what that means is the graph is going to come from down here. It's going to hit this x-intercept. It's going to fall below. Okay, and then it's going to come back up. Okay. Alright, we don't have any double roots. There's no exponents on any of these binomials or this expression right here. And so the cubic is going to look something like this. Alright, so let's use this graph to answer some more additional limit questions. Okay, so looking down here, evaluate the limits graphically, G, numerically, N, or analytically, A. Alright, so for G, okay, we're going to use the graph to help us answer this limit question. As x approaches -3, now remember, without the superscript, we have to consider approaching -3 from both the left and the right. So when you look up here, remember, this is a well-behaved polynomial function. So the limit is going to exist at any x value. So when you look at this right here, as x approaches -3 from the left side of the graph and the right side of the graph, you can see that the graph is going to be coming into that 0. Okay, so the limit is 0. I've got to draw faster. Okay, now numerically, this says to us, find the limit of this function as x approaches -3, and I've provided, yikes, a data table here. I don't know what's going on right here. Okay, that's supposed to be -2.9. I'll have to fix that in a later video, I suppose. Okay, numerically, the limit as x approaches -3 of this function. Well, what I've left here is some space for us to fill in the y values, okay, as we take turns putting each of these x values into the given function up here. Okay, and notice that these x values right here are approaching -3 from the left side. Okay, and then right here from -2.9 back to -2.99, etc., we're approaching -3 from the right. Okay, now I'm not going to take the time because with this video I'd have to keep it within 15 minutes. So, but what you can do is you can take the time to take each of these inputs and find the outputs in this expression right here. Remember, you can go to your calculator, type that into Y1. You can either use the trace feature on the calculator, or at the home screen you can evaluate the function using the proper keystroke. Okay. But I think you can see that once you do get these answers for each of these inputs, that these y values right here are going to be getting smaller and smaller, approaching 0. And then from the right, each of these values, okay, are going to be approaching 0 from the right-hand side. These from the left and these from the right. All right, so I'm just going to assume right here that that limit is also going to be 0. Alright, so for class the next time that we come together, have these notes completed with these values filled in, and then we'll check them together. Alright, coming down here, analytically, the limit as x approaches -3. Well, analytically, if you remember, is just trying direct substitution first, and if that works, wonderful, we're finished. If it doesn't, we're going to have to come up with some other plans. So right now, plug in -3, but as you can see, when you evaluate for -3 here and for x, you get a 0 factor. And then 0 times whatever number this would be, and this -3 right here is still going to give 0. So using the different approaches, we get the same limit. Okay. All right, and then what I did here was I said, let's consider the limit of the function as x approaches 0 from the left, and we're going to use the graphical approach. All right, so coming back up here, here's 0. It just kind of position yourself at x equals 0, but remember, you don't want to be here at 0. What you want to do is you want to approach 0 from the left. So all these x coordinates, okay, right here, are to the left of 0, and I'm getting closer and closer to 0. So two conditions have to be met. I have to be to the left of the x value, and then I have to be approaching that target x value. You can see the graph is going into the x-intercept there, so this left limit is 0. All right, numerically, we're going to evaluate the function at values that are smaller than 0 to the left of 0. So I have this data table, and again, based on our time constraints with these videos, I'm not going to take the time to fill in these values, but again, one at a time into the given function, evaluate and fill in the data table. And next time we meet in class, we'll look at those and check those. But it should confirm that these values in this data table are approaching 0. And they might be kind of interesting, like exponential notation or scientific notation, so we can discuss that in class. All right, moving down here, analytically, what's the limit of this function as x approaches 0 from the left? Well, okay, don't worry about the superscript just yet. Again, with the analytical approach, just go ahead and try direct substitution. Go ahead and plug 0 in everywhere you see x. Well, this will be 0. This factor will be -2, and that factor will be 3, but that product's still going to be 0. So all three approaches do result in a 0 when we're evaluating the limit as x approaches 0 from the left. Okay, same thing right here with this one as well. Graphically, as you approach 0 from the right, if you look back at your graph up above, as you come into 0 from the right, okay, the y values are going into 0. Numerically, again, fill in the data table. We'll check those in class. Analytically, just go ahead and plug in 0 everywhere you see x, and it confirms it is 0. Okay, and then what I did here, as you can see at the bottom here, is I said, okay, what's the limit of the function as x approaches 0? We've already considered from the left and from the right, and because the left limit and the right limit are equal, we can say the limit exists, and it is equal to 0. Whether we look at the graph, whether we put both of the previous two tables together and build one table here, the limit is still going to be 0. And it looks like this fell to the next page, so this should be, on here it's on the second page, but on your page, handout it should be on the first page. Hopefully. I hope so. Yeah. So that's also 0. Goodness, right faster. Okay. All right. Let's come back up here. Okay. This says graphically evaluate the limit of the function as x approaches 2. Well, again, 2 gives us another x-intercept, so graphically we're looking at the limit from the left and the right, and the graph suggests that we're going into 0. Okay. That point again doesn't have to be there for the limit to exist, but it does. It's a well-behaved function, so the functional value will equal the limit at any particular x or c value. Analytically, plug in 2. Well, you can see this factor becomes 0, so the whole answer will be 0. Okay, kind of transitioning here. The limit of the function as x approaches 1. We'll notice that up here on the graph as x approaches 1, here's 1 on the graph. Okay, the y values aren't going into 0. It's not a 0, an x-intercept, a root. And so it says graphically evaluate the limit. Okay, well, again, our options are, you should have this into y1 graphically. You can produce a window displaying this graph. You can press the trace key, press 1, and it should give you the y-coordinate that belongs to x equals -1. Okay? Or again, you can go to the home screen and evaluate y sub 1 or wherever you have it stored in at 1, and I believe the answer is going to be -4. So if you want to pause the video and check it, that'd probably be a good idea. Analytically, direct sub in, evaluate the function at 1. It is well behaved, so when we do plug 1 in, that functional value will equal the limit. So 1 times -1 times 4. Confirms to be 4. Okay. Okay. Now here's a big change right here. So I'm just going to kind of say, okay. Now look what happens. We haven't seen this before. This is new for us. Graphically, what's the limit of the function as x approaches positive infinity? As the x coordinates get larger and larger and larger, what are the y values approaching? Okay. This is another way to say we're considering end behavior. The extreme left or extreme right of the graph. What are the ends of the graph doing? It's end behavior of a polynomial function. So as x takes on very, very large values, okay, the further the graph goes to the right, think about where you're at on the graph, the y values just keep getting larger and larger and larger. Okay, so we say that that limit as x approaches infinity, oh goodness, okay, is positive infinity. Okay, numerically, okay, we can build the table. Okay, so let's consider that x is 10. Okay, fill that value in. Okay, let's consider that x is 100. Again, plug that in for every x in the original problem. 1,000, let's say x is 10,000. You'll be able to see from these values that as x takes on larger and larger values, the y's are getting increasingly larger as well. Analytically, we can still, even with this polynomial function, substitute in, as we did in the previous ones, we can substitute in infinity. So let's think about this. Infinity here, infinity reduced by 2, infinity increased by 3, doesn't matter. Positive infinity times positive infinity times positive infinity is going to result in, it's a little bit better, positive infinity. So we're looking at limits at infinity. So much of this is something we've already covered, but I wanted to add a new little piece. Okay? Graphically, the limit of the function as x approaches negative infinity. We'll go back to your graph. As x takes on smaller and smaller values, as x gets smaller and smaller, meaning it's going to the left, 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 what are the y values doing? Well, I know it's not a great graph, but my y values in that case, and behavior, are also getting smaller and smaller and smaller. Okay, so we're considering end behavior, and this limit graphically would result in negative infinity. The y's are going to negative infinity. Numerically, again, fill in the data table here. You can see that these values are getting smaller and smaller and smaller, and perhaps they'll be in scientific notation as well. So be on the lookout for that, like we discussed one of the first days together with the E notation. Okay. Analytically, evaluating this limit right here, again, you can plug in negative infinity here, plug in negative infinity here, and here as well. So this is going to look like negative infinity cubed, negative infinity times itself 3 times, and so a negative times itself 3 times is going to give you a negative infinity. And that confirms what we saw in the other approaches as well. Okay, gotta draw a little faster. Okay, at this point I'm going to stop the video, and I'm going to create another one because I see that I'm nearing the time limit of 15 minutes. We're going to look at the back together in just a minute in a second video. So I'll see you in just a second. Continuing our look at limits on the back of the worksheet, notice this new function, consider and graph the function f of x equals. And if you just look at it and observe what's going on with this rational function, in example 1 we were dealing with a polynomial function. Here we have a rational or ratio or fraction. We have a rational equation. Okay, but notice the similarity with example 1. Here what I've done is I've just inserted an extra factor in the numerator of x minus 2, but I've also included that common factor in the denominator as well. If we were to cancel these two factors right here, these common factors right here, we've seen this so far, okay, we know that the result there is that we're going to have a point discontinuity on our graph at x equals 2, at the 0 of that common factor we're canceling. So what we're left with is actually the polynomial function we graphed in problem 1, but we're going to need to remove the point at x equals 2 from that polynomial function. So we're going to have a 0 at x equals 0. Okay, now at x equals 2, we're not going to have a 0 because that's going to be where we're going to take out the point, but the rest of the graph will just kind of follow around that. And then x equals negative 3 is still a 0 as well. Okay, so function right here, and try and put in, oh goodness, got to draw fast, and then it's sloppy. Ooh, okay. I'm hoping to get better. Alright, so this is the graph of the function, the rational function that we were given right here. So if I look over here, I'm kind of going across instead of down right here. It says, what's the limit of the function as x approaches 2? Numerically. So we're going to fill in this data table. And again, I'm not going to take the time, but as you can see from the x values that we're approaching 2 from the left in this direction, and we're approaching 2 from the right in that direction. And you're going to, again, type this equation into one of your y equals lines. You're going to either press trace, or go to the home screen and find the y values belonging with each of these inputs. And what we're going to see is that at 1.9 on the graph, if we're at 1.9, we do have a y value. It's very, very small. It's a negative. It's small, close to 0. When you insert 1.99 to the equation, you're even closer to where x is 2, which is what we want to do, approach 2, and that y value is even yet closer to 0. So these numbers right here, the progression should indicate that we are approaching 0 from the left, and likewise these right here should indicate that we're approaching 0 from the right side, coming down this way. Okay, so we're going to say that the limit does exist, okay, and the limit is equal to 0, even though the point's not there. So this is probably a good place to kind of stop and put some things together. Remember we were talking about functional values, so I guess I'll come over here. Okay, what's the functional value of this rational equation at 2? Okay, we'll evaluate the function at 2, and what we're going to end up with is 0 in the numerator and 0 in the denominator. And think about what we call that. Okay, well, what that tells us is, in the functional value context, that f of 2 does not exist. It's undefined. Does not exist. Okay? Alright. So it's kind of interesting, though, what you can see here is that the functional value does not exist, but the limit does exist, and the limit is 0. Okay, so it's okay for the function not to be defined, and the limit still exists. And if you contrast that back up here with example 1, if you were asked on this well-behaved function, what's the functional value at 2? Okay, I gotta draw faster. Goodness, 2. The output is indeed 0. Okay, and then through this work down here, I think we saw, well, here it is right here, we saw that the limit of the function f of x as x approaches 2, goodness, is also equal to 0. And this will kind of help us in our study of the next topic when we look at continuity and what it means for a graph to be continuous. Okay, the functional value must equal the limit, okay, at any particular c value. Okay, so let's return to the back. There we are. All right, let's go to example 3. Okay, now look what I've done. I've created a piecewise function, and if you notice, this first piece right here is indeed example 2, but what I've done is I've included an additional point on our graph. I guess I'm not redefining it as a continuous graph, because I know that in order for that graph to be continuous, I would need to have a y-coordinate of 0. So here we just have an additional point at x equals 2, and that point falls at 2, negative 3. Okay, so graphing again, like we did in example 2, we have a 0 at negative 3, a 0 at 0. I wish it would let you linger. Okay, and again we have a point discontinuity at 2 because of the canceled common factor there. Oops. There we go. Oh, goodness. Okay, we're not done graphing this piecewise function. Now we're going to come back here and we're going to plot the point 2, negative 3. And that would be somewhere down here. Okay. Oh, my goodness. Alright, so let's come over here and look at this this question. What's the limit of the function as x approaches 2? The limit of the function as x approaches 2. And we're going to find that graphically. So as I approach 2, now remember, this is not equals down here. This is approaching 2. So think about a table of values as well. If x is at 1.9, and then it's at 1.99, and then the x-coordinate here, as I move closer with my right arrow, okay, as I'm tracing along the graph, if this is 1.99, 1.999, etc., my y values are going into 0. So what I can say is, okay, graphically, that I've considered the left-hand limit, okay, and let's just kind of look at that notation too. It wouldn't hurt. Oh, goodness. As I approach 2 from the left, okay, my y values are 0. They're going into 0. Let's look at the right-hand limit. Okay, as I approach 2 from the right, okay, these values of x are getting closer to 2. My y values, again, of the function, the functional values are going they're tending towards leveling off towards 0. Okay, and because the left limit equals the right limit, these two values are the same, we can say we've considered from both directions, and that limit is 0. Oh my goodness. Okay, but it's a good time to kind of stop and revisit functional values too. Okay, remember on this particular function, if you were asked, let's see if I can erase that. I hope. I don't know. Okay. That if I wanted to, oh goodness, come back up here. If I wanted to find the functional value at 2, okay, when you look at here at the piecewise function, remember the input's 2. Well, this is defined for all x but 2. Okay, but here in this piece, when x is 2, my output is -3. So the functional value is -3, the limit is 0. These two are not the same, and in our near future, we're going to see that when the functional value does not equal the limit, that there's got to be some type of discontinuity going on, and so our graph would not be continuous. All right, let's get example 4. Oh, goodness. You don't have this, don't worry about this page. Here we go. All right, now I'm going to kind of change gears. Consider and graph this function. Now, back from pre-AP, you do have notes G-3. I think it was G-3. So if you wanted to revisit this function from pre-AP pre-cal, I think you can look at G-3. And I also have double H2. That must have been a review with this function too. Anyway, last year in pre-AP pre-cal, we were actually looking at the parent function of absolute value of x over x. And this function kind of has some important implications for us in calculus. It's kind of interesting, and we'll look at that a little bit later too. But right now, revisiting this parent function right here, if I were to real quickly sketch its graph, you may remember, I think it was called a here and there situation. Okay, this y value up here is 1, and this y value down here is -1. And this means right here that for any x that's positive that we put into this function, the absolute value has no effect on changing the sign or anything. So the numerator would be positive, the denominator would be the same positive number. A number divided by itself is 1. So this is actually 1. And then likewise down here. If you put in a negative x value, here you're going to have a positive numerator and a negative denominator, and so opposites divide out into -1. So anyway, revisiting this function right here, what we see is if this is our parent function, that this is a shift left 2. So our point of discontinuity, which is a jump discontinuity, which we really didn't talk about last year, but now we can, our discontinuity is actually shifted to the left 2. So we still have an open circle here at 1 and an open circle here, oh goodness, at -1. So this is 1 and this is -1. Just that we've shifted that jump discontinuity over to -2, okay, because it's a transformation. All right. So this will kind of help us look at limits as well. Goodness. Okay, so let's, and don't worry about what's down here, that's another page and another day. All right, analytically, I think I'm going to skip around a little bit. Okay. Well, actually, I'll come back up here to graphically. Okay, graphically, we've got a picture of the graph. We can use that to help us get the limit question. Again, you can type that into your calculator somewhere on y equals and use the trace key. All right, if I approach -2, now notice there's no superscript, so I have to, it's my responsibility to look at approaching -2 from the left and the right. If I approach -2 from the left, that means the graph is down here. Well, what are these y values approaching as my x coordinates are getting closer to -2? Well, they're on that branch down there, so my left limit, if you will, okay, is -1. So it might be good to kind of come over here before we answer this question and consider the left limit. It's our responsibility. And the right limit. So approaching -2 from the left. What is it? Oh, g of x. We said that was -1 because we're going to be down here at these y values. And therefore, our right limit as we approach -2 from the right of g of x, as we approach -2 from the right, our y values are staying steady at 1. Okay, notice that the left limit is -1, the right limit is 1, this y value is -1, and this y value up here is 1. So it really kind of spells out a jump discontinuity. These two values are not the same, so as a matter of fact, we say the limit of this function as x approaches -2 does not exist. Okay, because the y values have to come into the same location, and they're definitely not. All right, numerically, again, we can fill in this data table right here by taking turns plugging these values into this function and filling this out. But I think we can kind of quickly fill this in. -2.1. If you evaluate the function at -2.1, your numerator is going to be -0.1, but the absolute value makes it +0.1. Our denominator will still be negative, so this will result in being -1. So you can confirm -2.1 is about here, so that must mean that our y value is -1. So anything that's to the left of -2 will result in a -1. And notice these input values right here are going to be to the right of -2. So when you do plug those in, you're going to get positive divided by positive, which is +1. Okay, moving along, running out of time here. The limit of g of x as x approaches -2 from the right. Well, analytically. Okay, well, what this means here is -2 from the right. Well, choose a number. Okay, I mean, you could plug in -2 to the function here and here, but you're going to get indeterminate, 0 over 0. So we might want to be a little more detailed. It didn't work here, plugging in -2, so -2 from the right. Well, again, -2 from the right would indicate maybe -1.999, and if we plug that in, okay, everywhere for x, we would see, it confirms with the data table that that's 1. As you approach -2 from the left, that would be one of these two x values, so those outputs would be -1. Okay, so therefore, I'm not sure why I don't have this here, but analytically, okay, without the whole data table, the limit does not exist. The limit as x approaches -2 of g of x does not exist. All right, and then real quickly coming down here and using this graph to help us answer these additional questions. What's the limit of this function as x approaches 5? Well, x equals 5 is over here, and I need to come into 5 from the left on the graph and 5 from the right, but it doesn't matter. This isn't an interesting place on the graph. X equals 5 isn't. It's just well behaved right here, so that's going to be 1. So if you want to kind of pause right now and kind of attempt these and then turn it back on and then check to see how you did, that might be a good idea. And of course we can have discussions about any of these the following day that we meet in class. As x approaches 0, here's 0, left, right, I'm on the +1 branch. -3 is over here. So as I approach -3 from the left and from the right, I'm still going to be on -1. Okay, as x goes to positive infinity, no matter what x value you're approaching towards infinity, you're still on the +1 branch, and this one's going to be -1. Okay, so just looking a little bit more at left and right hand limits, and just kind of looking at some other ideas with that too. All right.